Hi friends, in this session we study about the Poisson distribution. So here first I would like to explain the Poisson distribution is a discrete probability distribution and is very widely used in statistical work. It was developed by the French mathematician Simon Denis Poisson in 1837. Poisson distribution may be expected in cases where the chance of any individual event being a success is very small, where p is small. The distribution is used to describe the behavior of rare events such as the number of accidents on road, number of printing mistakes in a book, etc., and has been called the law of improbable events. Here I would like to explain how we find out the Poisson distribution. The formula of the Poisson distribution. Here you see the P of R is equal to e power minus m into m power r over factorial r. Here you see r, here is a variable, there are three components here, one is e, one is m, and third is r. So first I explained about the r. R is a whole number because it is the discrete distribution, so we will take 0, 1, 2, 3, 4 and so on. E is the base of natural logarithm, the value of e is 2.7183 and so on, and the only and final parameter m, the mean of the Poisson distribution. Here you see the m is equal to the mean of the Poisson distribution, which is equal to n into p, or the average number of occurrence of an event. So here you see the Poisson distribution is a discrete distribution with a single parameter m. We have a single parameter m. As m increases, the distribution shifts to the right. So this was all about the Poisson distribution. Now I would like to explain the assumptions for Poisson distribution. So look at here, the assumptions of Poisson distribution where we have to take the Poisson distribution is applicable. Poisson distribution used in place of binomial distribution when number one point is p is very small, n is very large or maybe infinite, and p is equal to m is a fixed number, n into p. N is the number of events, p is the probability of success. The product of this is equal to m, which is the mean, or we could say also lambda. Sometimes we use instead of m lambda, is a fixed number. This is the only parameter here. Now the one more thing I would like to explain you, the examples for random variable x having Poisson distribution, on which sort of problems you will apply the Poisson distribution. The number of deaths at a place in any year by an epidemic or by a rare disease. It is the, because this would vary, the ratio of this would be very low, very small ratio would be there. The number of mistakes per page by an experienced typist, the ratio of these mistakes would be very small. The number of typographical errors per page in a book printed in a good press, the ratio would be very small. The number of defective items in the items manufactured by a big factory, so the ratio of the defective item would be very small. The number of bacteria in a drop of clean water, the ratio of the bacteria in a clean water drop would be very small. The number of suicide per day in a city, where the ratio of suicide cases would be very small with respect to the population of the city. The number of the telephone calls per minute in a telephone booth. So in a telephone booth, the incoming calls would be very low per minute. So in these sort of problems, we could easily apply this Poisson distribution. Now friends, we see one example of Poisson distribution, how we get it. So first of all, we see how we get the Poisson distribution. Question 1 here, if 2% of the electric bulbs manufactured by a certain company are defective, find the probability that in a sample of 200 bulbs, less than 2 bulbs are defective. Or the second thing, more than 2 bulbs are defective. Two things we have to find out, and the given e to the power minus 4 is equal to 0.0183. So first I would like to say that the given percent p, the percent we have given, the percent of defective bulbs is 2%, and n is 200, n is 200, and defective bulbs percent is 2%. We know that we have only one parameter m. What we have to find out first. So in solution we see that m is equal to n p. We know that n is 200 here, so we put here 200, and p is, if we have to find out the p, so here p is equal to 2%, it means 2 over 100. So we put here instead of p 2 over hundreds. So look at here, these 2 will eliminate, and 2 into 2 is equal to 4. So we get here 4 is m we have. So they have given that the e to the power minus 4 is equal to 0.0183. This is the value of e to the power minus 4. So now we know that the Poisson distribution formula, P of r is equal to e to the power minus m to the power r over factorial r. So now we will find out P0, P1, P2, P3. This is all we find out, P0, P1 and P2. So we will find out first P0. We find out P0 is equal to e to the power minus 4 into 4 to the power 0 over factorial 0. So you get here only e to the power minus 4, because 4 power 0 is 1 and the factorial 0 is also 1. So you know that the value of this 0.0183. This is the value of P0. Now we find out P of 1. If there is one valve defective, we will find out P to e to the power minus 4 will remains m, and 4 to the power 1 over factorial 1. So we get here 0.0183 into 4, which would be 0.7320. Now we find out P2. P of 2, if the two bulbs are defective, then e to the power minus 4 into 4 square over factorial 2. So we get here 0.0183 into 16 over 2. So look at here, 2 1 time, 2 8 times here. So get here finally, it is finally 0.1464. So this we have got here. We don't know how many bulbs may be defective at any time. It may be more than 4, more than 5, more than 6, it may be 200 also. The 200 batch would be defective, but we have to find out according to this Poisson distribution. So we see how we get it. First thing, less than 2 bulbs are defective. So there may be no bulb is defective, or maybe one bulb be defective. So for first, less than 2 bulbs are defective. So it is P0 plus P1. So we find out these values. P0, we know that it is 0.0183, 0.0183, and P1 we know that here 0.7320. So we get here, so it is finally 0.7503 is the probability of the bulbs which are less than 2 are defective. More than 2 bulbs are defective. The second point we have, more than 2 bulbs are defective. Two bulbs are defective. So look at here, we know the complete probability is 1. So for this, 1 minus P of 0 plus P of 1 plus P of 2. So we get here, so we will write here 1 minus 0.0183 plus 0.7320 plus, and P of 2 we know that it is 0.1464. 0.1464. So we see here 1 minus, if we add these all, we get here, finally we get here the summation of these all three, 0.8967, and if we subtract it from 1, we get 0.1033. So the probability of the bulbs which are defective more than 2 bulbs, the probability of the defective bulbs more than 2 is this one. So in this way we could easily find out the probability distribution through this Poisson distribution, where the population parameters are not given and we have to find out the expected frequency distribution. We could easily find out through this. So this is a way, it's very simple to find out this Poisson distribution.